Hey guys, we're in week 4. Good job. We are wrapping this bad boy up. I think we're getting close to being finished. Um, in fact, we may be in week 5 already. Are we? Are we in week 5? Hey, anyway, let's get to the point. Let's go over a quick review of NTFS that we covered last week, and then we're going to dig a little bit deeper into the master file table as promised. So, if you look up here next to me, you will see we have FTK Imager, and this is actually not live. This is just a PowerPoint that I did previously. So you can see that we have here in the root directory, we've got all the $ attribute files from the NTFS file system in the root directory. These files are indicative of NTFS. That's how you know for certain that that's what you're looking at. Let's take a look specifically at the MFT or $MFT, the master file table. Here's what it looks like in hex. And if you zoom in a little bit, you can see we've got here a series of attributes within each entry of the master file table. We're looking at the first entry of the master file table. We know this is the first entry in the master file table because if we look down here under the name attribute, we actually see $MFT, and we know that the MFT is the first entry in the MFT. Okay. Over on the left-hand side, you will see your file offset or byte offset counters. And in FTK Imager, it's very nice because you can toggle back and forth between hexadecimal and decimal. It's currently in hexadecimal, and you can see that. And as you know, hexadecimal is base 16. We've got 16 rows across the top, right? So that's 16 bytes. I said rows, I meant columns. 16 columns across the top. And so this first offset right here is indicated by this offset counter here to the left. It's 0. So this would be 0, this would be offset 1, this would be offset 2, this would be offset 3. So offset 0, 1, 2, and 3 are known as the file entry signature or header, and you can see that those are ASCII for FILE or file. The 0 there is just this 30 here. It's the same for every entry. And one of the things that I like about FTK Imager is if for whatever reason you get confused by hexadecimal, you can switch back and forth the file count or file offset counter over here from decimal to hexadecimal and back and forth. It's just a toggle. But before we go on and show you the decimal version here, you'll notice that this next row down starts with hex 10. Well, what's 1 times 16? It's 16. So these are bytes 0 through 15, and here's byte 16 or offset 16. And right here it's depicted as hex 10. Here's hex 20. What's 2 times 16? It's 32. So this is offset 32, 33, 34, 35, 36, and so on and so forth. And that's how you would count, use the offset counter in hexadecimal. All right. If I right click on it, it pulls up this little menu. I can click, toggle back and forth between show decimal offsets, and as you can see, now it takes us the same exact. We're looking at the MFT entry in the MFT, and you can see the offsets down here are now in decimal or regular base 10 counting. And sure enough, this is offset 16, this is 17, this would be 31, next one down here is 32, this would be 47, next one down here is 48. And so the counter here gives you the number of the byte or the number of the offset in this first column all the way down. And we just know that then this one would be 17, this one would be 18 and 19. You know, this one's 224, this one's 225, 226. So, all right, hopefully that's clear as mud now. All right. We've already indicated that there's the file signature for it. It tells us right there at this offset, right? So we're at 16, 17, 18, 19, 20. At offset 20, that tells us how long the header is, okay? And that is in hexadecimal, not in decimal. So we know that this is not actually 38 bytes, but it's hex 38 bytes. And we could say, what's 3 times 16? That's 48 plus 8 is 56, right? So we can do that in our heads and say that that's 40, that represents the length of the file entry header is 56 bytes or hex 38 bytes. If you don't want to convert it in your head to decimal, that's kind of cool because we know we can just count out 3 rows, 1, 2, 3, 3 times 16, and then go 8 more bytes, and that is the end right there. That's 56 bytes, or hex 38 is the 56th byte right there, and then so we know that our first actual attribute starts right there with this header, attribute header of 10, not 10, that's decimal. This is hex 10000000. Okay, and so, but that highlighted area there represents our file entry header. All right, so most of you did that well on the assignment. Good. This next entry here, this next header information that you see there, starting with 10, hex 10, is our standard information attribute header. So uh, it's a very useful attribute to know about. The byte immediately following the header, the 60, tells us how long that entry is in hexadecimal. So how many bytes is 6? Well, what's 6 times 16? I don't even know off the top of my head. I should know that, but I don't. So I'm just going to count 6 rows starting here. This 10 is the beginning. So this 48 will be the next 16. This FB is the next. So here's 1, here's 2, here's 3, here's 4, here's 5, here's the 6th row of 16. So if we go all the way to the end, 16 bytes, there we go. This next section here, starting with hex 30000000, is the next metadata attribute within this entry of the MFT. And that's again, that's how we know where the next entry starts, because right here this 60 tells us that this first metadata entry or metadata attribute is hex 60 bytes long. And so we would go back and start at the beginning of the file header entry and go forward 60 hex bytes, and that's where this what we would call the standard information attribute ends. And we know that a new attribute is beginning right here with this hex 300000. Uh, excuse me. So the next thing in we see here, this is significant, is the hex 18. Well, that tells us where the first metadata entry for that file starts. So how do I know? What are we talking about? Well, hex 18 is here's 1 times 16, and then 8 more, these next 8 bytes, and then we get to the beginning of the metadata itself. So hex 18, or 1 times 16 is 16 plus 8 is 24. So 24 bytes in, we get to the next entry within that standard information attribute. And so we're going to look at these first 8 bytes. These are significant for us, starting with FB and ending with 01. It looks like my red circle is over the top of that. But these next, there's 4 8-byte strings, and those are significant. They represent the timestamps of the file. There's 4 timestamps. There's a created timestamp. There's a let's see, is it I know what they are. I'm just trying to remember what order they're in here. Created is first. I believe modified is second. I believe the entry, so the entry itself. So these first 2 timestamps represent the timestamps for the file itself, the data out on the hard drive that represents the master file table. And then this third one is just the master file table entry when it was updated. And then these last 8 bytes here represent the last access time, which may or may not be updated regularly, okay? So we're going to go down here and take a look at our hex value interpreter. And that's really useful information when we're looking at these byte strands, because FTK Imager does a great job of parsing out those 8-byte strands for us. So how do we do it? Well, we highlight the first 8-byte strand starting with FB and ending with 01. And this is recorded in little endian. So if we were to do this calculation manually, we would calculate it from right to left: 01, David 1, Frank David 3, Bravo 96, 2670, Frank Bravo. We'd put that in our calculator, or heaven forbid, if we had to actually do it longhand with a pencil and paper, I might have to shoot myself. But we don't have to do that because FTK Imager has a hex value interpreter. And if we highlight those 8 bytes, then it tells us right here in UTC time that it is 12:40 p.m. on August 23rd of 2016. So that's when that file was created on this media. Okay. Something that you need to know about file created time is it's when it was created on this particular file system, not necessarily so. And in this case, we're looking at the master file table, the record for the master file table. So that should be pretty consistent because it's only been created on this system. I guess in a weird circumstance, you could take a master file table file from another system and copy it to this file system, in which case it wouldn't be entry level 0. It would be some other arbitrary number, entry number in the master file table. But I digress. What we're looking at here is the master file table entry, the time it was actually created on this system, which is very useful because this is effectively going to tell us very, very close to the time, date, and minute when this particular operating system or file system was formatted. Okay, when it was formatted. And that's key, because you may have to do a timestamp analysis on a file sometime, and if a bad guy tries to reset the BIOS, that could screw up all of your time indicators, but this time will be pretty accurate. This is when the master file table was created. Okay, other files other than the master file table. Let's say it's a Word document, and let's say I copy or I create a Word document on my system. Well, it's going to create an entry in the master file table for that Word document, and these first 8 bytes in this in this attribute right here, this standard information attribute, these first 8-byte sequence of timestamps here are going to tell us the time that that file was created on that system. So if I created that file on another computer and then thumb drived it over, plugged it in, and transferred the file over to this system, the created time would be when I transferred it over to this system. So it's the time that the file was created for the first time in the master file table on this file system. So that could be confusing to people. Why? Because let's say I've been working on this Word document on another computer for months, and the last time I modified it was a month ago. I created it 6 months ago. I modified it a month ago, and today I decided to USB drive it over to my other computer, and I plug it in, and I drag it in here, and I drop it onto my file system, and it creates a new created time, which is after the last modified time, which is this next sequence we'll look at right here, this FB7026963B. Now you notice it's identical for the master file table. The last time it was modified and the last time that it was the time it was created. So that's unique to the master file table. Most other files will have a modified time that's later than the created time. Okay. Now, the exception is if I create a file on another on another computer and then bring it over here and drop it on here, the created time could be newer than the modified time, and that throws some people like, wait a minute, how can you create a file after it's modified, or how can you modify a file before it was actually created? Well, that's why, because these timestamps are relative to the time it was created on this media, and the other metadata may transfer over with the file, so it may have a modified time that's different. Now, let's talk just really quickly about UTC time. I know this isn't all relevant completely to the master file table into the NTFS file system, but I do want to clear up any questions that you might have about UTC time versus local time. In Arizona, UTC time or local time is 7 hours behind UTC time. What's UTC time? Well, if you're military, it's the same thing as Zulu time. You've probably heard it called GMT time or Greenwich Mean Time. So Zulu time, Greenwich Mean Time, or UTC, Universal Time Code, are really all saying the same thing, and that's what time it is, you know, in Greenwich, England. The prime meridian runs through Greenwich, England, and that's what time it is when the new day starts at midnight. Relative to all other time zones, it's midnight there, and we're 7 hours behind that. So if it's midnight in Greenwich, England, it's 5 p.m. the day before here in Arizona. So we're behind. We have to catch up. And so when it's 7 o'clock in the morning in Greenwich, England, it's just barely beginning to be midnight of that same day here. Okay, so you can see there's a 7 hour time difference here. Uh, on this master file table, and FTK Imager does a nice job of parsing out those two different times, and that's of course because FTK Imager is using my local time for my computer. It doesn't know that I'm in Arizona. I mean, I guess it knows kind of that I'm in Arizona, and that it's just looking at my BIOS and saying, oh, you have -7 in your BIOS, so that's your local time, and we're just going to calculate it for you. Okay. This next one is the modified time. We're going to do the same thing. We're going to read the highlight it and read it little endian style right to left. And it's, as you can see, it's the same times down there, same exact times, but it won't always be the same exact times. That's just in the case of the master file table record for the master file table. Other files will often have very different times from the modified time and the created time. Now, we're now looking at the next attribute down, right? So if you go back here, we're looking at the standard information attribute, which starts with hex 10. Now we're going to go down here, these hex 60 bytes down to this where it starts with hex 30. So now we've got that highlighted. That's the file or the metadata attribute header for the file name attribute. The file name attribute, and the file name attribute contains a lot of the same information as the standard information attribute, which we just looked at. You'll notice if you look there, you'll notice those same 4 strands or strings, 8-byte strings. Those are timestamps, and they're probably going to be the same as the timestamps in the standard information attribute, but they are updated differently and under different rules, so they are not always the same. Typically, when doing forensic analysis, we will look at the standard information attribute for timestamps because it is most frequently and most regularly updated. The timestamps in the file name attribute area don't follow all the same rules and do not update as frequently, so we would not use the timestamps in this attribute in most cases for a forensic examination. All right, so there's our attribute length indicator, hex 68. So we know we're going to go 8 over and then 6 down, and that's why we've got this block highlighted yellow. And then we're going to go down here and take a look at what's really relevant to this, and that is simply the short file name header. It's right there, MFT, $MFT. And it's in Unicode, so you notice it's got these 00s between each of the names of the attribute. If you look over here in the ASCII text column, you'll see $, .m.f.t. And those are the dots are the zeros, and that's called Unicode. It gives 2 bytes for every character, and that allows for a lot of different font signatures for different languages, which may require additional information per character. So that's universal, or not universal, that's Unicode, but we can still read it right here in plain text. That is $MFT, and that is a really useful way to locate files manually. Is we just right click over here in the ASCII text and type in the name of the file we're looking for, and we'll go down through the master file table until we find it, if it exists. Okay, so that's really useful. If we go down now to the next file attribute, you'll notice if I go down, hex 68 rows, or that's 6.5 rows down, we get to what we see here is this file, a metadata file header called the data $data attribute, which starts with hex 80 followed by zeros. All right, so this is the third attribute, which is most important in reading the master file table. We know that this attribute is 6 rows long, starting from the beginning of the attribute header, and so we've got them highlighted there. We'll take a look at that. This is the 10 is a flag that tells us that it is non-resident. Okay, so we've got that could either be a zeros or it could be 01. Zeros would mean that it is a resident uh, file. In other words, all of the data from the file itself is actually included here in the master file table entry. Really rare that you would have the entire file contained in the master file table. Because as you know, each entry in the master file table is how long? Typically only 1024 bytes, so it's 2 sectors. So unless it's a very small text file, um, it's going to write the actual data to the file out somewhere else in the data areas of the hard drive, right? Somewhere in the clusters out allocated for data. Very rarely will you see the entire file. The entire file would have to be probably less than 600 or 700 bytes in order for it to fit into the master file table, because the master file table entry is only 2 sectors, so it's just barely over 1,000 bytes. And to include all of the metadata attributes that we're looking at right now and the data for the file itself has to be like 600 bytes, like really small. Okay, so could a very small text file be a resident file? Yeah, and so if you've got a text file that just has a password or a couple of passwords or a passphrase or a sentence or something like that written in it, then when you save it, it doesn't put that file anywhere out on disk other than right here in the master file table. So all of the data would be included here in this data chunk. But in this case, we see the flag 01, which tells us that it's a non-resident. In other words, the data for the file is not resident, doesn't live, doesn't reside in the master file table entry. It resides out there on the disk, out there in the allocated clusters, somewhere out on disk. Um, and 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 uh, and that's what that 01 flag means, is that the data is too big for to be contained in the master file table. Now, I'm not going to go into I've given you a lot to digest. I think we're already at 23 minutes here today, so that's a pretty good lecture. Later this week or early next week, I'm going to go into the specifics of how to go out and find data out on the hard drive when it's non-resident, and it gets pretty interesting. This is where we're getting now into some really good nuts and bolts of the NTFS file system, particularly the data attribute of the master file table. There's a lot of juicy details included in this little chunk that we're looking at right now. But I don't want to overwhelm you. We've already talked about the standard information attribute and how we can parse out the timestamps, including the four metadata timestamps that are critical for timeline analysis: the created time, modified time, the entry, and the last access time. So those 4 timestamps, we looked at those 4 8-byte strands and how to parse them out. Maybe I had to go back and reiterate a little bit more about what that means. But we talked about that. We talked about the file name attribute starting with hex 30, and how it just basically contains the ASCII or the plain text version of your file name, and that makes it very easy to find file names within the master file table. And then we talked a little bit here about this one, the $data attribute or hex 80 header, and how it's got this flag here that lets us know if all the data is going to be in the attribute itself or if it's going to be out on disk. In this case, it's a 0, 1 flag, so that tells us that it's out on disk. All right, just a preview of what we'll talk about in the upcoming week. This 40 here tells us the position of so this is at offset relative to the start of this attribute. Okay, so starting from the hex 80, the header 80000000 that's highlighted up here, relative to the start of that, hex 40 bytes in, or 4 rows in, is where we're going to get to our first, our starting location of our data. That's why it's called the $data attribute, because it tells us where on disk the data starts. Okay, and if it's contiguous, if it's a contiguous file, if it's all stored in clusters that are, butted up against each other, there's no clusters in between them of other files. If it's a contiguous file, then you'll just have one data run in there. If it's a non-contiguous file or if it's a fragmented file, then there will be multiple data runs here, and we'll have to figure that out. Okay, but the first data run here starts at 4 rows down. Okay, so I've got my first row, second row, third row, fourth row, and here, this right here, this hex 33 is the beginning of our first run list, it's called. Okay. And there it is. And we see our first run list, and we know our first run list is 6 bytes long. Okay, how do we know that? Well, the first 3 bytes represent part of the run list, and the second 3 bytes represent the next part of the run list. Now, this is not supremely important for this week, but I'm just trying to give you a preview for later this week. And then there's our next run list, and this one is going to be 7 bytes long. Okay, so we're going to get into that more, but that's what's coming. Okay, I think that's all I've got for you today. I did want to touch one more time on parsing out these timestamps. And this is just really a bit of trivia. I don't know that it's really relevant. It could be relevant. You may have to explain how you parsed out this run list someday. You may be sitting in court, and it may be really important for you to describe to the defense attorney or to the prosecution or whoever you need to explain, the jury or whatever, how this time is calculated. Well, if you just parse this out as a straight number, if you just start at hexadecimal and convert it to decimal, right? So I got to my calculator and I put in 01 David 1 Frank David 3 Bravo 962670 Frank Bravo. It's going to give me this gigantic number up here, this signed integer that I have no idea how to even pronounce this number. I know we've got, let's see, 500 million, so there's 296 billion. Here's 164 trillion. So here's 131 quadrillion, I guess is the proper terminology for a number that big. So 131 quadrillion, 164 trillion, 296 billion, 534 million, 454,523. That's the integer that this hex value represents. Okay. Well, what the heck is that number, and how do we get a date from that? Glad you asked. That is the number of 1/100ths of a second. The number of 1/100ths of a second since midnight of 1601, January 1st, 1601. It sounds arbitrary, sounds bizarre. It has to do with calendar epochs and stuff that I don't completely understand. I just know that that is the number of 100,000ths of a second since January 1st, midnight, January 1st, 1601. And that's how you get the date of August 23rd, 2016. And so could you, in theory, manually parse that out. I challenge you to do that. Wouldn't that be fun? What a great project to manually parse that out. Now, there are other tools I think we discussed in previous lectures called Decode, for example. Decode's a great little utility that somebody programmed. They did the scripting to describe that basically does that little algorithm. It converts the hex to decimal and then converts the 100 thousandths of a second into current times by adding all of those seconds to January 1st, midnight, 1601. All right, there you go. There you have it. There's forensics of the master file table data, metadata attributes, including an overview of the standard information attribute, the file name attribute, and the $data attribute, which we will dig into deeper next time to actually find out how to go out onto the disk and find the data. Glad you took this class. I'll bet you are also glad you took this class. Hang in there.